we consider how to measure vectors. We want to find the length of a vector and also the distance between vectors. We use a common uh, math um, measurement called the so-called distance formula, which is based on, and to some degree, the dot product. And we see the dot product kind of creeping into all of the concepts. The next section deals with the inner product and inner product spaces. The dot product is a subcategory of the inner product. My notation all the way through will be the notation for a true inner product. I think the book uses a dot, and I will use a different notation which represents the inner product. So here are the objectives for this section. We look at the length of a vector, the distance between two points, between two vectors, the dot product. We look at the angle between two adjacent vectors, determine orthogonality, verify the Cauchy-Schwarz inequality, the triangle inequality, and then the Pythagorean theorem the way it was introduced at first. Well, first the length, and some of this will be commonplace to most of you. You've seen it in other places, and so that's a good thing. So the length of a vector is called the length or the norm of a vector. V, and V is has n components, so it's in Rn, and so the norm is given here. We also call this length or this norm the magnitude. Now, if the norm of V is equal to 1, then V is said to be a unit vector. In Calculus 3, we talk about making a unit vector by simply taking the vector and just dividing it by its norm, and it becomes a unit. That is, its measurement is 1 as well. So we look at that, and so that's a pretty cool thing. So here V divided by the norm of V, which if we take the norm of it, that gives us 1 as well. The length of a scalar multiple, if V is a vector in Rn and if C is a number or a scalar, then the norm of C times V can be represented by extracting or pulling out that common scalar, but we take the absolute value of it times the norm of V. What I'm going to do is just go through all of these definitions and theorems, and then after that, at the end, we'll look at the problems. Here, let V be non-zero. You don't want it to be 0 because you're computing its norm downstairs, and if V is 0, its norm is also equal to 0, and you don't want to divide by 0. So, and I just talked about the unit vector a couple of slides ago, but here it is. We say that this vector u is the unit vector in the direction of v. That's pretty cool. In Calculus 3, we talk about directional derivatives, and it's based on the same concept. The distance between two vectors, if we have two vectors, u and v, here they're only looking at u and v in the 2 space. That's most unfortunate. But it's better to look at the distance in Rn, and then we can always extrapolate down to n equal to 2. They use n equal to 2 as a model, and so you get the just the common distance formula from algebra, right? We can write this distance as the norm of u minus v, and so that's the same thing. So this is the distance between u and v. Next, we have the distance between two vectors in terms of that distance formula. And I just said that. Sorry about the squeaking chair. Promise that I'll fix that right. So the distance between u and v is the same thing as the norm of u minus v. The dot product and the angle between two vectors, to find the angle theta between two non-zero adjacent vectors u and v. Notice that the norms of the vectors is the length, right? So we can find the so-called angle by using the law of cosines to the triangle here that's shown. Now, later on, we'll talk about in this section how to find the angle theta, right? So here I just want to introduce the concepts, and then we'll dive into deep waters in just a minute. So the definition of the dot product of u and v, where these two vectors are in Rn, is said. Now my notation is the inner product of u and v, and so and most of us have seen that before. So that just becomes u sub 1 times v sub 1 plus and so on, plus u sub n times v sub n. Here are some properties of the dot product. Here, u dot with v, or the inner product of u and v, is the same thing as the inner product of v and u. So this would be the commutative property. Here, the dot product of u distributed on the sum of v plus w, so this is the distributive. Here, this idea of c times the dot product of u and v is the same thing as saying c times u and then that dot with v. Same thing as saying u dot with c times v. Now this would be the idea of the associative property. And then we have just for us to know that we have some similar terms, that the dot product of u and v is the same thing as the norm of v to be squared. Remember that norm of v is the square root. So you have that norm of v, which is the square root of v sub 1 squared plus and so on, plus v sub n squared. So if I square this norm, then I'm squaring that square root, and so you end up with v sub 1 squared plus and so on plus v sub n squared, which is just the inner product of v with itself. And then here, the inner product of a vector with itself is positive or equal to 0. And here the inner product is 0 if and only if the vector v is 0. So we have the idea here of positivity. The Cauchy-Schwarz inequality. So here, if we have two vectors u and v, it is to be understood and also proven indeed by Cauchy and also later on by Schwarz, that the absolute value of the inner product of u and v is less than or equal to the norms of u and v multiplied. So we get back to something that I had raised earlier, and that was up here in terms of to find the angle between the two vectors. So the angle theta between two non-zero adjacent vectors, right, and Rn can be found using here that cosine theta is equal to the inner product of u and v divided by the norm of u times the norm of v. Theta is on the interval from 0 to pi. Two vectors are said to be orthogonal if their inner product or if their dot product is equal to 0. The triangle inequality. In a lot of these concepts, I'm not going to take too much time to prove these consequences here in this presentation. For my students, you can look in Blackboard in the old content. There, I believe it's labeled as chapter 6, but you'll see where I've proven all of these consequences. The triangle inequality, if u and v are vectors in Rn, then the triangle inequality says that a triangle has three sides. So the sum of two sides is always greater than the third side. It doesn't matter what sides you choose, by the way, as well, too. So here we have this side, we have this side, and, well, we have the translation of v over here, so we can form the triangle. And then this side here is that norm of the sums of u and v. So we call this triangle inequality. Pretty cool concept also. Now lastly, the Pythagorean theorem. The Pythagorean theorem is based on vectors that are orthogonal. If these two vectors u and v in Rn are orthogonal, then we have this norm of u plus v to be squared is equal to, we don't have inequality, is equal to the norm of u squared plus the norm of v squared. And here we have two illustrations. Let's now look at some problems so we don't get, so you don't get sleepy. So let's first, for part A, let's find the norm of u. So u is given, so it's going to be simply the square root of that -1 to be squared plus the 0 to be squared So this is negative 1 to b squared plus 0 to b squared plus 2 to b squared plus 1 to b squared, and it's the square root of all of that. So we get 1 plus 4, which is 5 plus 1, we get the square root of 6, right? Part B, the norm of V. So this is that 3 squared plus the 1 squared plus the 0 squared plus the 1 squared, and then we take the square root of all of that. So that gives us 9 plus 1 plus 1. We get the square root of 11. Oh, there it is right there. And then the norm of u plus v is equal to the norm. We add those two vectors together, so we get negative 1 plus 3, the corresponding components, gives us 2. 0 plus 1 is 1. 2 plus 0 is 2. And then 1 plus 1 is 2. Now we take its norm, so that gives us the 2 squared plus the 1 squared plus the 2 squared plus the 2 squared. So we get 4, 8, 12 plus 1 is 13. So we get the square root of 13. So that all checks. Find the distance. So the distance of u and v is the same thing as the norm of u minus v. So let's do that. So we have the norm. Look at these two vectors and let's get the subtraction. So u minus v is 1 minus 4. That's negative 3. 0 minus negative 1 is 1. 2 minus 1 is 1. So now we take the square root of these terms raised to the first power and then summed. We get the square root of 9 plus 1 plus 1, so that's the square root of 11. So now verify Cauchy-Schwarz inequality for vectors. Remember, this theorem says that you have the absolute value of the inner product of u and v is set to be less than or equal to the square root, well, the norm of u times the norm of v. So we first find the inner product of u and v. So that becomes the 4 times 3 plus 3 times the negative 2. So we get 12 minus 6, that gives us 6. And also note the inner product is a scalar. So the inner product is just a number. So here the inner product of u and v is always an R1. Right? Now the norm of u, so this is the square root of, look at the vector u, its components 4 squared plus 3 squared. So we get the square root of 16 plus 9, 25. So that just gives us 5. Now the norm of v is the square root of the 3 squared plus the negative 2 squared. So we have here 9 plus 4, we get the square root of 13. I just have to, I know the answers are there, but I don't know, I just have to still write it. So we draw here the following conclusion. The inner product, let me just write this out with the numbers. So here this absolute value is what they wanted. So it's positive. So we have this inner product that we got 6 is less than, this becomes 5 times the square root of 13. Is 6 less than 5 times the square root of 13? Yes, it is. So we get indeed less than, so we can verify that the Cauchy-Schwarz inequality for the vectors holds for these vectors. And I want to say I think for this problem I think it always holds. I think you're always going to get that. I hadn't ran across anything otherwise. Uh, Find the angle theta between the vectors. So for there we need the inner product of u and v. So that's the 3 times the 4 plus 4 times that negative 3 plus 1 times 0. So that guy gives us, this inner product gives us 0. Anytime we get 0 for the inner product, that means that the two vectors are orthogonal. Orthogonal means perpendicular. So that just tells us that the angle theta is 90 degrees. And you can write that as pi over 2. So here that formula says cosine theta is equal to, now this is not the absolute value, it's just the inner product of u and v divided by the norm of u times the norm of v. So who needs to compute the bottom when you got the top that's 0? So if the two vectors are orthogonal, then the dot product equals to 0. And that means that we have orthogonality. The two vectors form a 90-degree angle. Find the angle theta between the vectors. Since that one was easy because that numerator was 0, let's do this one and see if we can get it. So we need the inner product of u. Oh, that yellow is good to my eyes. And I apologize for the backdrop being black, so that students who are printing out the PDFs is rough with the black backdrop. I'm going to try to see if I can investigate that and see if I can try to help you out. I'm so sorry about that. The black is good for me with the backdrop black is good for me with my vision. I just went through 5 eye surgeries, and so with trying to get everything corrected with laser and then some complications. So the backdrop being black and then writing with yellow preferred and sometimes the red is good for my vision. So I apologize for others who may be having some issues. So the inner product of u and v, so this is 2 times negative 4, oh that's pretty, plus 3 times negative 1. So we get negative 8 minus 3, so we get negative 11. So now we need the norm of u, which is the square root of the 2 squared plus the 3 squared. It gives us the square root of 4 plus 9. Gives us the square root of 13. Now the inner product, well, the norm of v, sorry about that, getting ahead of myself. So this is the square root of the negative 4 squared. Is that a negative 4? Is that a 2? Hey. Plus the negative 1 squared. So that's the square root of 16 plus 1. So we get the square root of 17. So now cosine theta is equal to the inner product of u and v divided by the norm of u times the norm of v. So here that gives us the negative 11 over the square root of 13 times the square root of 17. So that gives us on our, just on a calculator, is negative 0.7399. But that's not theta. We take the cosine inverse of that. So theta is equal to cosine inverse of this number. And that gives us for the angle 137.7263 degrees. Since they want this in radians, right? So we times that by pi over 180 for that conversion, and that gives us 2.404 radians. Determine whether u and v are orthogonal, parallel, or neither. If they're orthogonal, it means that the dot product is equal to 0. If they're parallel, the two vectors are scalar multiples of each other. Two vectors are parallel if they are scalar multiples of each other. Okay. So to see if they're scalar multiples, that's, I mean, you can just look at them and tell that, right? Just an example. If I have 2 and 3, and then let's say 4 and 6, right? Just for an example. So you see that they're scalar multiples. So you'll be able to see if the vectors are indeed scalar multiples of each other. So here for this problem we just take the inner product. So that gives us the negative 2 times 1 over 4 plus 7 times negative 7 over 4 plus 6 times 0 plus 0 times 6. So this inner product, we get negative 1/2 here minus 49 over 4. And I'm just going to just leave that as 2 over 4 since we have the same denominators. So we get negative 51 over 4. And this guy is not equal to 0. So you can tell that the vectors are not scalar multiples of each other, so they're not parallel. Since the inner product is not equal to 0, they're not orthogonal, so it must be neither. Right? So that's that. Well, let's keep digging. Does the triangle inequality hold for the vectors u and v? Well, let's go back and restate that triangle inequality, right? So the triangle inequality says that the norm of u plus v is less than or equal to the norm of u plus the norm of v. So if that be the case, we got to find all three of these values. So first, the norm of u, so that's the square root of that negative 3 to be squared. That's the square root of 9, we just get 3. Then we look at the norm of v, so that's the square root of that 1 squared plus the 2 squared. So we get the square root of 5. Now we need the norm of u plus v. So this is the norm of, I'm going to add u and v, so that gives us 1 and negative 1. So we find its norm, that's the square root of 1 to be squared plus the negative 1 to be squared. And that gives us the square root of 2. Okay. So with that said, we have, based on this theorem, the triangle inequality, we get the square root of 2. Is it less than or equal to? And it's the question mark. Here the norm of u, which is 3, and then this is plus the square root of 5. So the question is, is that the case? So just on your calculator, let me pull mine out. So we have the square root of 5, which is 2.236 plus 3. So that gives me on this side 5 point, it's approximation 236. Then that square root of 2 is like 1.4 something. So indeed, 1.4 is less than 5.236. So say yes. Right? So that's the triangle inequality. Well, one more problem. So here we verify the Pythagorean theorem for the vectors u and v. So for that Pythagorean theorem, it says this, that the norm of u plus v to be squared is equal to the norm of u squared plus the norm of v squared. Okay? So we got to find these three quantities. So here they want you to compute u and v to determine if they're orthogonal, because the Pythagorean theorem is only based on vectors that are orthogonal. So we have the inner product of u and v. So this is that negative 4 times 0 plus negative 2 times 1 plus negative 1 times negative 2. So that gives us negative 2 plus 2, we get 0. So yes, it's orthogonal. So since that's the case, then we compute the three values. This norm of u, the norm of v, and the norm of u plus v. So the norm of u would be the square root. And if you don't mind, I just go ahead and plug in those values. So this is 16 plus 4 plus 1, right? I don't need all that. So that gives us the square root of 21. That yellow doesn't show up so well on the white. And then the norm of v is the square root of, you get that 0 squared, right, plus the 1 squared plus the negative 2 squared. So we get the square root of 5. And then the norm of u plus v. So that's the norm. We add the two vectors. Negative 4 plus 0 is negative 4. Negative 2 plus 1 is negative 1. And then negative 1 plus that negative 2 is negative 3. So we compute this guy. So this is the norm of negative 4 to be squared is 16, plus negative 1 to be squared is 1, plus negative 3 to be squared is 9. So that gives us the square root of 26. So when we square those values, so we get the norm of u to be squared is 21. The norm of v squared is 5. The norm of u plus v squared is 26. Well, they wanted the vector, the sum vector, the sum of the two vectors, so we got that there. Negative 4, negative 1, and negative 3. And then the norm of u plus v to be squared, we got that to be 26. So then we verify equality. So we get the norm of u plus v to be squared, which is 26. Is that equal to the norm of u squared, which that's 21, plus the norm of v squared, which is 5, gives us 26. So yes. Well, I'm going to stop there. I think that should be enough for right now. And if you have any questions, just let me know.